Okay, now that we've looked at the technique of finding the estimate of the instantaneous rate of change using preceding and following intervals, we're now going to look at the centered interval approach. So to fill this out, the estimations of instantaneous rate of change, yada yada yada, can be found using the centered interval approach, as we're going to see right here. So a family purchases a home for $125,000, where that would be, I have no idea, perhaps in the Arctic Circle for that price. And so the home price appreciates following this formula. H of t is the value of the home, t is the number of years that the family owns the home. What we want to do is estimate the instantaneous rate of change in the home's value at the start of the 8th year of owning the home. So for the estimation of instantaneous rate of change, sorry, I didn't leave enough space there for you to write that all out. What we want to do is we want to go to the same amount of the same length of time on either side of the 8-year mark. So we want to go have t between 7 and 9 years, and then we're going to calculate average rates of change like we've been doing between different values of t1 and t2. So first we're going to say t1 is 7 years, and t1 is going to increase toward 8, and we're going to let t2 equal 9 years and decrease towards 8. Okay, so take a look at the table here. What I'd like you to do is then follow this pattern and continue filling out the information here. So h of 9 is the t2. We're going to substitute that into the formula for h here and for t. Do that calculation. Remember to do the exponents first and then multiply by 125,000 afterwards. Then substitute in t1, which is 7, and plug that in. Do the calculation. Here we have the two values, then we're going to subtract them to get 23,231.09. Because we're using money values, we're only going to 2 decimal places. When it's not in terms of monetary or financial scenarios, then I'd like you to round to 7 decimal places so we can get the greatest accuracy possible. And then of course here we'll do the delta t, which is t2 minus t1 in this case, which is 9 minus 7, gives us 2. Then we'll take this value of 23,231.09 and divide by 2 for delta h over delta t to give $11,615.54. That is the average rate of change, the average appreciation of value of the home between 7 years and 9 years. Okay, then we're going to change 7 to 7.5. It's going to increase towards 8. And we'll change 9 to 8.5, which is then decreasing towards 8. We'll take those two values, we'll sub them back into the formula, in for t, and we'll get these values here. And we'll subtract here, of course, 8.5 minus 7.5 for the delta t is 1. So when you divide, you just get that value again, $11,610.62, which is the average appreciation of, or sorry, the average rate of appreciation of that home between 7.5 years and 8.5. Then we'll change the T1 and T2 to 7.9 and 8.1, so we're getting closer and closer to 8 from both sides. And then we do the same calculations, divide by 0.2, because that's when we divide or subtract these values of t, we get 0.2. Then we'll divide here to get that value, and we'll just continue on that. Okay, so please pause the video and do all those calculations, please. Now I'm just going to let you continue on with those calculations as opposed to me giving them away. But we will fill in this final part here. That in this example, the average rates of change were calculated using intervals that had 8 as their midpoint. The endpoints of the secant slowly move toward the midpoint, thus resulting in an estimate of the instantaneous rate of change. Of the appreciation of the home at year 8. Okay, so I won't give it away, but you should see in the last couple should narrow in on the exact value that it would be. Okay, now yet another way, a third way of finding the instantaneous rate of change, or estimating the instantaneous rate of change, is using the difference quotient. And the difference quotient is worth putting little reminders around, because that's the one that's going to be the most important for you to know for the rest of this course and into calculus, should you choose to take that course. So this technique is basically the same as the other techniques of using preceding and following intervals. However, the only thing we're going to be doing is using small values of h that are either added or subtracted from the, as I read my notes, from the target value in the calculations. So that means that h is the tiny horizontal distance between 2 points P and Q. Okay, so what I mean by that is we've got point P here, and point P is at some specific value of A and f of A, so some x value that we know, and the y value of that function is found by calculating the function, the value of the function at that point A. So that's point A, f of A, which is, of course, x1 and y1. And then point Q is what we're going to say is A plus H, and f of A plus H. So it's that specific x value plus a tiny amount, either above or below, either to the right or to the left of that point P. Okay, so in this case, just for the demonstration, the diagram purposes, the point Q is going to be to the right of P. So in this case, we'll be adding a tiny value of H here. And of course, this is then x2 and y2. Okay, so when if you were to take or calculate the slope between these 2 points, PQ, along the secant, we would of course do y2 minus y1 over x2 minus x1. We do exactly the same thing as this, but instead of using y's and x's, we're going to be using f of a plus h, f of a divided by a plus h minus a. Okay, so here is some value a, the x value, and here is some x value a plus h, which means that between the two is the horizontal distance, is that tiny little distance between the two x values. That is some distance h. Okay, so that's what h is. It's just the horizontal distance between the two x values of these 2 points. And of course, as point Q gets closer along the curve towards point A, the distance between them, the horizontal distance between point A and point A plus H, gets smaller and smaller as H gets smaller and smaller. Okay? But obviously as Q, or this distance between the 2 points, gets smaller, this point Q rides down along the curve towards P. Okay? So if we're to find the slope, or the average rate of change between 2 points, like I said, we'd have y2 minus y1 over x2 minus x1, which can then be calculated as f of a plus h minus f of a, which we see here in the numerator, divided by a plus h minus a. Well, if you have a plus h minus a, the two a's will cancel out and you're just left with h. Okay, and that's what we see here in the note.